back at it. Cool beans. Cool beans. All right. So yeah. Okay. So for this, we're gonna have to use strong induction, as regular induction is not good enough here. So again, same premises. We're gonna need our inductive hypothesis saying assume this holds for yada yada yada. So assume this just set a limit on it because again it can't be less than 8. But we'll just say A is less than N and N is less than K. Messes up. Assume this statement is true for all N. 8 to for all N for all and such that if I'm messing this up, 8 is less than N and less than K. Okay, we'll leave for now, I guess. What do they say here though? Yeah, okay. We want to show N plus 1 is true. Okay. So let's do it. So let's say N plus 1 has to be expressed as a sum of N 3x plus 5y. I'm missing something here. I'm just writing such that doesn't really fit in grammatically, but I'm not really showing this to anyone but you guys. Okay. My money to a Bosch. Oh, I guess. Yeah. Okay, so let's try this. I did have to look at the answer for this one below. Slow, I guess. Oh, I swear this is wrong though. What do they do here? Oh, shoot, guys, I'm sorry. This makes sense. So n plus 1. N plus 1 can be simplified to n minus 2 plus 3. Didn't really, there's nothing funny there, nothing like crazy. Literally just rearranging the addition. Excuse me. Now, we know that n minus 2 is covered by our hypothesis. So, because n minus 2 falls between 8 and k, it must be true that we can kind of group these terms together. So, n minus 2 is equal to So, as I was saying, and I clearly forgot, like a fucking idiot, I was messing up because I was writing it as kind of like the final answer. But we don't want that. We don't want the final answer. We want, same way as we do other induction problems, we start with what we have, and then we kind of simplify it as we go along, right? So n minus 2 can be expressed as a sum of 3x plus 5. So 3x plus 5 plus 3, and we just group the 3's together. So my fault, I should not have already wrote it as x and y, because that it would be incorrect, that would be wrong. So what we want to do is kind of have what you, start with what you're, I usually like to do the case that I'm given, but you can start with the beginning sometimes and kind of manipulate it to get to the final thing, but you can do this sometimes. And then, yeah, simplify from there. Probably always going to have to use your inductive hypothesis. Again, I'm only first year, so I don't know if there's any induction problems where you don't. But yeah. Again, this manipulating the addition trick is actually quite helpful in most cases. So yeah, keep that in mind. Five and 3. All right, let's continue. Okay. We have exercise 3 and 4. So I guess we'll do exercise 3. Okay, so consider a 2-player game consisting of 2 bowls of marbles. Each player takes a turn removing any positive number of marbles from a single bowl. The player that removes the last marble wins. Show that if both bowls have an identical number of marbles, the player who goes second always has a winning strategy. Okay. So, base case. Okay, so base case. Okay, I'm gonna go bowl my way back. In my head. Okay, so both bowls have n marbles. Player 1 goes first. So yeah, I don't really know how to do the base case for this, to be honest. But player 1 takes a marble. So in a case where they both have 1 marble, player 1 takes a marble first. Now only bowl 2 has a marble. And player 2 takes the marble from bowl 2. So now there's 0 marbles left. So by definition of the game, the player that removes the last marble wins. So player 2 removes the last marble, so they win. Okay, so I'll come back to this. Okay. Now we're gonna go with our actual induction step. Hey Matthew. Okay, so we claim that the player 2 always wins if each bowl has an identical number of marbles. So to show that, we can say assume that. So I guess we'll bring it to like cases. So we'll say case 1. If the bowls have an equal number of marbles, then player 2 wins. So then player 2 wins. Okay, so now we can do a second case. Case 2. Or I guess we'll say constructor 2. Don't mind my spelling constructor. Constructor 2. If the bowls have an equal number of marbles, then player 1 wins. Okay, why does player 1 win? So if we consider it, right? If 2 of the bowls have an unequal amount of marbles, and the game is just starting, then we can say that player 1 takes player 1. Okay, yeah. So player 1 takes all the marbles from one of the bowls, or takes all the marbles that have now, like the imbalance of marbles. Like we'll say one bowl has 10 marbles and the second one has 15. We claim that player 1 always wins this because what player 1 can do is player 1 can take 5 marbles from the second bowl, and now both of the bowls have an equal amount of marbles. This is important because now this relates back to our first constructor. So now player 1 has become player 2 because he's moving second, and player 2 has now become player 1 because he is now the first person that is moving with an equal number of marbles in each bowl. So now we can say that if both players are playing rationally, that being like if you're trolling or whatever, then obviously we can't predict what you're going to do. But if both players are playing to win and know what they have to do to win, then player 1 will always win if there's an unequal number of marbles in the bowls. So this is going to be tricky to write down, but we'll try it anyways. Okay, so if player, so we didn't have to say, so if the amount of marbles in the bowls are equal, then player 2 always wins. Because again, this fits our first constructor, and we don't need to do any more work. We're done. Player 2 always wins. Now, if the amount of marbles in the bowls are unequal, then player 1 always wins. So here we have to explain. Just it's not immediately apparent, and we didn't prove it in our base case. Okay, so okay, the amount of players are equal, then player 1 always wins. So on the first move, player 1 always equals, always takes the positive, takes a positive integer of marbles from the bowl with a greater amount such that the bowls have an equal amount of marbles. Okay. Now, one wins. Okay, cool. Okay, so exercise 4. Show that every positive integer has a binary representation. That is, every positive natural number can be uniquely written as a sum of distinct powers of 2. Okay. So base case, n is equal to 1. So we want to show that 1 can be expressed as a power of 2. Simple. 1 is equal to 2 naught. 2 0. To the power of 0. And then you get 1 is equal to 1. So this base case holds. Okay. So induction step. Not 8, sorry. For all values of n, where n is a natural number, and it's greater than 0, but less than k. Cool. Now, we can say we want to show n plus 1. Okay. So n plus 1. So that 2 is, sorry, so power of 2. As a sum? It said sum, right? As a sum of distinct powers of 2. Okay. Okay. So we want to show n plus 1 can be written the same way. So, and note that n plus 1 can be rewritten as n minus 2. No. As n minus 1 plus 2. Via the inductive hypothesis, n minus 1 can be written as a sum of unique powers of 2. Plus 2. So then we can say this will just become 2 to the power of 1, or 2 plus 2 is 2 squared. So either way, we have 2 is now equal to n plus 1. So since n plus 1 can be expressed as a power of 2, then and 2 is obviously a power of 2, then obviously their sum should also be able to be expressed as a power of 2. This is also not correct. It's partly not correct. Thus, n plus 1 can indeed as a power of 2. Where obviously all of these numbers do not equal each other. Another way you could do this, actually, which actually might be a more correct way, is n plus 1 is equal to n plus 2, 0. So, note that 1 and n can be expressed as unique powers of 2. Via the inductive hypothesis, right? So now we've got to complete the uniqueness part of the proof. So assume that two numbers, or assume that one number has two different unique what do you even call that? Unique sums of 2. However, since both n and 1 are unique via the inductive hypothesis, then n plus 1 must also be unique. So, probably stop here for today. Pick it up tomorrow. Thank you for watching. Goodbye.